Have you ever poured yourself a hot cup of coffee and wondered how long it takes for it to cool down to that perfect sipping temperature? Or maybe you have thought about how forensic scientists estimate the time of this based on body temperature? This question leads us to an interesting concept in physics known as Newton's law of cooling.
Hello everyone, my name is Noradila binti Muhammad Zaimi, and today we are going to explore Newton's law of cooling.
A principle that not only explains how objects lose heat but also has real-world applications in fields like forensic science and engineering. So, let's dive in. First, let's take a quick trip back in time. In 1701, Sir Isaac Newton discovered that the rate at which an object cools is proportional to the temperature difference between the object and its surrounding. This means that if you have a hot object in a cooler environment, it will cool down faster than if it were in a warmer one. The mathematical expression for this law is simple yet powerful. The derivation temperature over derivation time equal to negative K multiplied with T minus TA. T is the temperature of the object, TA is the ambient temperature, and K is a constant that represents how quickly the object cools. But why does this matter? Understanding how quickly things cool down can help us in many ways. For example, forensic scientists can estimate the time of death by measuring a body's temperature. And engineers use this law to design better cooling systems for machinery. Now, let's look at what happened over time. When we plot the temperature against time, we see that initially the temperature drops quickly but then slows down as it approaches the ambient temperature. This is what we call as exponential decay. Next, let's explore Newton's law of cooling using Wolfram language. First, we define the constant and parameters. The ambient temperature, capital TA, is set to 25 Celsius. The initial temperature of the object, capital T naught, is 80 Celsius. And the cooling constant K is 0.1, which controls the rate of cooling. Next, we write the differential equation. TT equal to negative K TT negative TA, which describes the rate of change of the object temperature over time. Here, TT represents the rate of temperature change, and the term negative KTT minus TA shows that the cooling rate is proportional to the difference between the current temperature and the ambient temperature. To solve the equation, we also specify an initial condition T0 equal to T0, which states that at time T equal to 0, the object starts at its initial temperature of 80 Celsius. Using the dissolve function, we find the analytical exact solution to this equation and extract it into a usable function, T analytic T. Additionally, we use the and dissolve function to compute a numerical solution, which provides an approximation of the temperature over a specified time range from T equal to 0 to T equal to 50. This allows us to compare the exact analytical solution with a numerical approximation. Finally, we plot both the analytical and numerical solution on the same graph. The plot style option is used to differentiate the two solutions with different line, style, or colors for clarity. In our graph, the blue lines represent the analytical solution, while the orange line represents the numerical solution. The plot table option is used to add a title to the graph, in this case, Newton's law of cooling, to provide context. The axis label option allows us to label the axis, where the x-axis labeled as time t to represent the passage of time and y-axis is labeled as temperature T to represent the object temperature. Lastly, we include a legend using plot legend, which specify the names of the two solutions, analytical solution and numerical solution, for easy interpretation of the graph. From the graph, we observe that the object temperature decreased exponentially over time, eventually stabilizing at the ambient temperature of 25 Celsius. The alignment of the blue and orange lines shows that the numerical method provides a highly accurate approximation of the exact analytical solution, validating the accuracy of the model and its implementation.
It is fascinating, right, to see a principle discovered 300 years ago still hold relevance today. In summary, Newton's law of cooling help us to understand how objects lose heat over time. Whether you are enjoying your coffee or analyzing crime scenes, this law plays a crucial role in our daily life. That's all from me. Thank you, and don't forget to like my video, okay?